In section 3.5, we're looking at this idea of a sum to infinity, and before we can talk about that, we need the idea of a divergent and a convergent sequence. So with geometric progressions, divergent and convergent sequences aren't deceptive. Outside of geometric progressions, they are very deceptive. Things that look convergent and that look divergent perhaps aren't what they look like. But with geometric progressions, it works like this. This is a divergent sequence. I can tell it's a divergent sequence because the terms are getting bigger. If I added up 2 plus 4 plus 8 plus 16, eventually I'm going to get an infinitely large number. Okay, that's what a divergent sequence is. If you add them up, you're going to get an infinitely large number. A convergent sequence, look at this one. If I do 1 plus a half plus an eighth plus a 16th, well, I'm going to get a number which is, it's going to get closer and closer to 2, isn't it? But I'm never quite going to get to 2. Okay, that's the idea. So this is a geometric series. If I add it up, it gets closer and closer to 2. The terms in the sequence are getting smaller and smaller. The sum to infinity is called, the sum to infinity is what we get if we get the number that this is getting closer and closer and closer to. So it's getting closer and closer and closer to 2, so the sum to infinity of this sequence would be a 2. Okay, that's the idea. So, as I say, with things which are not geometric sequences or geometric series, in general, convergent and divergent sequences aren't always what they seem. They can be a bit counterintuitive, but with geometric series, it's what you think. So if the terms are getting smaller, it's a convergent sequence. If the terms are getting bigger, it's a divergent sequence. So terms are getting smaller when mod r is less than 1. If mod r is bigger than 1, then the terms get bigger. So convergent and divergent for that. Now if r is equal to 1, then the sequence is just the same number over and over again, isn't it? So it would be something like 2, 2, 2, 2. That would be an r equal to 1 sequence. And that, if we're going to call it a geometric progression, which we kind of can, it's a geometric progression with a common ratio 1, then it would be a divergent one. So we can put a greater than or equal to symbol on there. Okay. So we want to ask ourselves, right, well, how is this going to fit into A-level questions, and what sort of thing they're going to ask us? Well, what they're going to ask us is, what is the sum to infinity of this sequence? Is this sequence convergent or divergent? Well, is it convergent or divergent? Easy, just look at the common ratio. Okay. What is the sum to infinity? Well, that is, the sum to the first n terms is a 1 minus r to the n over 1 minus r. When n gets bigger and bigger and bigger, we get the sum to infinity. So we write down sum to infinity equals, it's the limit as n tends to infinity of this thing. So what does this thing get closer and closer to as n gets bigger and bigger? Now remember, we only have the sum to infinity if r is a number smaller than 1. If r is a number smaller than 1, and when I say smaller than 1, I mean mod r is less than 1, then r to the power of n gets smaller and smaller, doesn't it? And it gets closer and closer to 0. So the limit as n gets to infinity of this is a times 1 minus 0. So a times 1, or a, over 1 minus r. So the sum to infinity is a over 1 minus r. Now, even though this is a bit of a fiddly area of maths with lots of complicated bits in it if we study it properly, when it comes down to the A-level questions, they're not too bad. They're things like, example 15, there is, it tells us we have a geometric series. It tells us the fourth term and the seventh term, and it says show that it's convergent. Well, if it tells you the fourth term, you do AR cubed. If it tells you the seventh term, you do AR to the sixth. You've got the fourth term, it tells you, the seventh term, it tells you, and you write those two down and you've got simultaneous equations. Now, as it happens, in example 15, these are nasty decimals, so it's going to be a bit fiddly. We're going to have to use a calculator. So I'm not bothering putting those numbers down here. I'm just showing you the principle. We can find A and we can find R. We can see, though, if I do now put these numbers in, 1.08 and 0.23328, well, this is the fourth term, this is the seventh term. As I go along the sequence, the numbers are getting smaller, the size of the numbers is getting smaller, so it has to be a convergent sequence because I know it's a geometric progression. If it's not a geometric progression, then the terms getting smaller is not enough to say it's a convergent sequence. But if it is a geometric progression, the terms getting smaller is enough to say it's a convergent sequence. So if it was in an exam, I'd actually have to find R and show that R is the size of R is less than 1. But if I wasn't in an exam, then we can see it by just saying, well, the terms are getting smaller, so it must be because it's a geometric progression. It then asks us to find the sum to infinity. Well, from solving these two equations, you found A and you found R. So you just say, well, in that case, the sum to infinity is A over 1 minus R. Just use the formula, okay? And so on. So that maybe they will give you the sum to infinity, and they'll give you R, and they'll say what was the first term, or whatever. It's another formula to use. So even though sort of philosophically, mathematically, this is quite a complicated area, the questions they're going to ask us on it aren't going to be too bad on the A-level exam. That's the end of 3.5.